quantum mechanics. I'm going to share the stream with Discord and see maybe if anybody wants to talk about it like while I'm streaming. Did I just lose internet? I did not. Alright, so I started out with the introduction to quantum, well, let me back up a little bit. Quantum mechanics is the article that I started off on, and that got me to Introduction to Quantum Mechanics, and that's the main article that I've been reading through. So many aspects of quantum mechanics yield unexpected results, defying expectations and deemed counterintuitive. These aspects can seem paradoxical as they map behaviors quite differently from those seen on larger scales. In the words of physicist Richard Feynman, quantum physics quantum mechanics deals with nature as she is. Absurd. Features of quantum mechanics often defy simple explanations in everyday language. One example of this is the uncertainty principle. Precise measurements of position cannot be combined with precise measurements of velocity. So that's like Zeno's arrow paradox. You've got something that has a specific position in space, right? And the closer you get to measuring to where it is in space, the harder it is to measure its velocity. So you're either going to have to swap one for the other, I think. Or you can just never precisely measure velocity as long as you're measuring something in space. Another example is entanglement. A measurement made on one particle, such as an electron that is measured to have spin up, will correlate with a measurement on a second particle. An electron will be found to have spin down if the two particles have a shared history. This will apply even if it is impossible for the result of the first measurement to have been transmitted to the second particle before the second measurement takes place. What? Alright, so what is spin? So that redirects to spin in physics, and it says spin is an intrinsic. I know what intrinsic means, or do I? In science and engineering, an intrinsic property is a How is it that this Wikipedia, how is it that like the core Wikipedia articles, like if you go to quantum mechanics, which is like the foundation of everything, and you go to something that is like one of the first like references to an article, and then you go to the first reference in that, and the first reference in that, and you go to an article like this where it talks about intrinsic and extrinsic properties, and you get a message that says this article needs additional citations for verification. Like, don't you think maybe that should be a priority? Like, Wikipedia is, how long has Wikipedia been around? 2001. You've had 24 years to get your references together for something that is this basic. In science and engineering, an intrinsic property is a property of a specified subject that exists itself or within the subject. Okay? An extrinsic property is not essential or inherent to the subject that is being characterized. For example, mass is an intrinsic property of any physical object, whereas weight is an extrinsic property that depends on the strength of the gravitational field in which the object is placed. I'm not going to read this whole article because it's probably going off on a tangent. It's short, so I can read the whole thing. I'm still not going to, though. It's like, I get it enough. Okay, spin is an intrinsic form of angular momentum carried by elementary particles, and thus by compound electrons, atomic nuclei, and atoms. Spin is quantized, and accurate models for the interaction with spin require relativistic quantum mechanics or quantum field theory. I don't know what angular momentum is. This is why it's called a Wikipedia crawl stream, just because I keep going from thingy to thingy. Angular momentum, sometimes called moment of momentum or rotational momentum, is the rotational analog of linear momentum. Okay, I get what linear momentum is. Linear momentum is just when you have something that's going in a straight line. It is an important physical quantity because it is a conserved quantity. So this is redirecting to an article on conserved quantities or conservation laws. It's redirected to conservation laws. The total angular momentum of a closed system remains constant. So I'm going to assume that a closed system is something that is a thing where everything is intrinsic. It is a conserved quantity. I should probably read the thing on conservation laws. In physics, a conservation law, this is a conservation law article. In physics, a conservation law states that a particular measurable property of an isolated physical system does not change as the system evolves over time. Okay, so you're saying it's changing and it's not changing. You need to make up your mind there. Okay, they're saying that the system is isolated and yet it's changing over time. So it exists in and of itself, like separate from other things. Exact conservation laws include conservation of mass energy, conservation of linear momentum, conservation of angular momentum, and conservation of electric charge. There are also many approximate conservation laws which apply to quantities such as mass parity, lepton number, baryon number, strangeness, hypercharge, etc. These quantities are conserved in certain classes of physics processes, but not in all. I feel like maybe I ought to be studying more about conservation laws, like in order to be able to understand bigger concepts. Alright, so probably ought to learn about linear momentum just because that's the simplest thing and I supposedly understand it. I'm gonna put on socks, it's cold in here. It's 70, I set my thermostat on 71 degrees, but I think that's really mainly only for when I'm sleeping. Like 72 is more where I'm comfortable at, and I think most people for 72 is where they're comfortable at. It's like when I'm awake, 72 is comfortable, and when I'm asleep, 71 is comfortable. A local conservation law is usually expressed mathematically as a continuity equation, a partial differential. I don't know what a continuity equation is. A partial differential equation which gives a relation between the amount of the quantity and the transport of that quantity. Why do they have transport in quotation marks? It states that the amount of the conserved quantity at a point or within a volume can only change by the amount of the quantity which flows in or out of the volume. Why are you specifically going after volume when there's a whole bunch of other stuff? Or is volume just kind of a universal thing? It states that the amount of the conserved quantity at a point or within a volume can only change by the amount of the quantity which flows in or out of the volume. At a point. What are they talking about at a point? I have one viewer, but keep in mind you can't enter in any texts until you've been subscribed for, or not subscribed, until you've followed me for a month. That's just because I don't want to spend voice chats or streams moderating stuff. I want to actually just have non-trolls like on my channel. Like you can message in Discord on the chill lounge text on the in there. I think it's transmitting. Oh, oops. All right, I think it's now transmitting in the Discord chat. Although I think you could just mute one and listen to the other. It'd probably be better if you just listen in on the Twitch channel and obviously speak in the Discord. Okay, let's try to read this again. A local conservation law is usually expressed mathematically as a continuity equation. I don't know what a continuity equation is. Partial differential equation, I don't know what that is either, which gives a relation, and so now they're defining it, right, which gives a relation between, am I even supposed to be doing this? Shouldn't I be like trying to sell stamps on eBay or something? I get frustrated at stuff. Why am I not logged in? It says a local conservation law is usually expressed mathematically. I'll wait until the siren goes away. See any stars from here? I don't think I can. Okay. I get frustrated at stuff because, like, I hit a point at which I stop understanding something and the explanation of something stops. So all I can really do is just stop and think about a thing. local conservation law is usually expressed mathematically as a continuity equation, a partial differential equation, which gives a relation between the amount of the quantity, like what? Can you give an example of like a quantity of something? And the transport of that quantity. Well, that's one thing, right? And why do you have transport in quotation marks? They don't say why they have, like, okay, if I had written this, I'd have said between the amount of the quantity, parentheses, example, close parentheses, and the transport of that quantity, parentheses. This is why we put transport in quotation marks. Okay, so between the amount of the quantity, so 3 arrows, and the transport of that quantity. 3 arrows going through space, but that's not a closed system. It's like, okay, you're explaining it, but you're not explaining it. It's like it's written as a summary for people who already know what they're talking about. Like, it's supposed to be an encyclopedia, but it's not. It's missing the puzzle piece. See your little globe with the puzzle pieces, and it's missing puzzle pieces. Well, you didn't put a puzzle piece there. I'm just gonna sit like L. What if L's name is just something like Leonard? It states that the amount of the conserved quantity, okay, so 3 arrows at a point, so 3 arrows in space, or within a volume, 3 arrows within a space of like a meter, can only change by the amount of the quantity which flows in or out of the volume. Well, then you're talking about no longer a closed space or a closed system. You're talking about something going from a closed system to an open system. There's a guy who wrote a YouTube video about just stopping trying to understand something and just skipping something and coming back to when you will try to understand it, and just focusing on the things that you can understand. But I mean, this is pretty basic stuff. Don't you think maybe I ought to try to understand this? It states that the amount of the conserved quantity at a point or within a volume can only change by the amount of quantity which flows in or out of the volume. It does not make sense. the article on conservation of linear momentum. Okay, from Noether's, it's Noether, and so I think that's a long A sound. From Noether's theorem, every differentiable symmetry. From Noether's theorem, every differentiable symmetry leads to a local conservation law. Other conserved quantities can exist as well. Conservation laws are fundamental to our understanding of the physical world, in that they describe which processes, I think it's processes if you're talking about a possessive, in that they describe which processes can or cannot occur in nature. For example, the conservation law of energy states that the total quantity of energy in an isolated system does not change, though it may change form. Okay. So you've got an arrow that's facing to the right and an arrow that's facing to the left. It can either swap directions, but it's just still only going to stay one arrow. In general, the total quantity of the property governed by that law remains unchanged during physical processes. You're not talking about a quantity of objects, you're talking about a quantity of a property. So like an arrow weighs six grams. Let's just say 6 grams. You've got an arrow that weighs 6 grams. Feels like it's been way longer than half an hour. Where was I going with that? In general, the total quantity of the property governed by that law remains unchanged during physical processes. Okay, so you've got a 6 gram arrow, and you've got a physical process, which is it's in flight, so it's going to weigh 6 grams no matter what. Right? Is that what you're saying? With respect to classical physics, conservation laws include conservation of energy, mass or matter, linear momentum, angular momentum, and electric charge. With respect to particle physics, particles cannot be created or destroyed except in pairs, where one is ordinary and the other is an antiparticle. With respect to symmetries and invariance principles, 3 special conservation laws have been described associated with inversion or reversal of space, time, and change. just got distracted by the linear momentum article, which redirects to the article on momentum. And it's not even the top of the article, it's the section on conservation. I will read that later. I never learned this stuff in school. I never took any course on physics, I don't think. I don't think I've ever taken a course on physics. I've taken courses on algebra, biology, chemistry, but I've never taken a course on physics. And I feel like maybe that's what I should have taken like a long time ago, but I never got taught that. Conservation laws are considered to be fundamental laws of nature with broad application in physics as well as in other fields such as chemistry, biology, geology, and engineering. Oh boy. Poincaré. Most conservation laws are exact or absolute in the sense that they apply to all possible processes. Some conservation laws are partial in that they hold for some processes but not for others. One particularly important result concerning local conservation laws is Nather's theorem, which states that there is a one-to-one correspondence between each one of them and a differentiable symmetry of the universe. What does differentiable mean? What does the universe have to do with this? Okay, are you just saying like the universe universe is a closed system, right? Is that what you're trying to say? The universe is a closed system? Because I'm pretty sure that's not true. Like, because the universe is infinitely expanding out into nothingness. So it's an open system. But you're saying within that cloud of the universe, things are symmetrical. So that's a differentiable symmetry. So you've got the arrow, it's flying through space, it's had the momentum put into it by something that was symmetrical, like, you know, there was energy being transferred into the arrow that's contributing towards this momentum. But there's been, how's there 10 minutes since I started on this one little segment? So there's an arrow, it's flying through space. In this particular closed system, it's had differential symmetry in that, you know, momentum was imparted to it, but like there was energy that was expended to do it, so it's a trade-off. So it's symmetrical. Like, because there's energy inputted to it from the bow. So it's symmetrical, but it's differentiable. I think that makes sense. Ah, what? Somebody just popped in and out. For example, the local conservation of energy follows from the uniformity of time, and the local conservation of angular momentum. Look, angular momentum directed to conservation law. Now you're momentioning angular momentum. You need to just stay on topic. For example, the local conservation of energy follows from the uniformity of time, and the local conservation of angular momentum arises from the isotropy of space. In other words, because there's no preferred direction of space. So isotropy just means it's the same everywhere. Local conservation of angular momentum just means that stuff is the same everywhere. In other words, things are consistent. Notably, there is no conservation law associated with time reversal, although more complex conservation laws combining time reversal with other symmetries are known. So basically they're saying there's no associated conservation law with time reversal, except when there is. Exact laws, and then they have a list of the exact laws. A partial listing of physical conservation equations due to symmetry that are said to be exact laws, or more precisely, have never been proven to be violated. And then this section has no citations at all. This is like basic stuff. How do you not have any citations here? Alright, what should I read next? Should I continue trying to read this article? Because it doesn't make any sense. Because they talk about conservation laws as fundamental laws of nature. Then they list the exact laws that they're talking about. They say exactly, this is exactly what we're talking about here. So I should probably try to understand it. Slug is a unit. Slug is equal to about 32 pounds, or 14.59390 kilograms. Why do they have that 0 at the end? Inch version of the slug equal to 12 slugs has no official name. But is commonly referred to as a blob. It is equivalent to 386 pounds or 175 kilograms. That's a heavy weight. Like, Like, I know bullets are referred to as slugs sometimes. But they don't weigh 32 pounds. I mean, they do at least 32 pounds of force. Okay. A partial listing of physical conservation equations due to symmetry that are said to be exact laws, or more precisely, have never been proven to be violated. Conservation of energy, capital E, but it's in italics. And the respective Nather symmetry invariance is time translation invariance. Getting sleepy. Translation of time along t-axis. Nobody has mentioned what time translation invariance is. Conservation of linear momentum, lowercase p, but it's a bold p. Yeah, I'm definitely getting sleepy. Is space translation invariance, or Poincaré invariance. Conservation of angular momentum is L equals R times P, which is the conservation of linear momentum, rotation invariance, rotation of space along XYZ axis. Conservation of boost 3 vector, bolded capital N equals T italicized, bold lowercase p minus italicized capital E times R is the Lorentz boost invariance. The Lorentz boost of space-time along XYZ axis. Conservation of electric charge is U parentheses 1 close parentheses lower script or subscript capital Q gauge invariance. This is going nowhere. Is translation of electrodynamic scalar potential field along v-axis in phase space. Conservation of color charge is SU3C gauge invariance, translation of chromodynamic potential field along RGB axis in phase space. Conservation of weak isospin, SU2L gauge invariance, translation of weak potential field along axis and field in phase space. Conservation of the difference between baryon and lepton numbers B minus L, U1, B minus L gauge invariance. Another exact symmetry is CPT symmetry, the simultaneous inversion of space and time coordinates, together with swapping all particles with their antiparticles. However, being a discrete symmetry, Nather's theorem does not apply to it. Accordingly, the conserved quantity CPT parity can usually not be meaningfully calculated or determined. also approximate conservation laws. These are approximately true in particular situations such as low speeds, short time scales, or certain interactions. Conservation of macroscopic mechanical energy, approximately true for processes close to free of dissipative forces like friction. Conservation of rest mass, approximately true for non-relativistic speeds. Conservation of baryon number, see chiral anomaly and Svalerion. Conservation of lepton number in the standard model. Conservation of flavor, violated by the weak interaction. Conservation of strangeness, violated by the weak interaction. Conservation of space parity, violated by the weak interaction. Conservation of charge parity, violated by the weak interaction. Conservation of time parity, violated by the weak interaction. Conservation of CP parity, violated by the weak interaction. Conservation of CPT symmetry in the standard model. I don't know what any of this stuff means. I'm reading this off, but I don't understand what any of it means because they're not explaining it adequately. The total global and local conservation laws. The total amount of some conserved quantity in the universe can remain unchanged if an equal amount were to appear at one point A and simultaneously disappear from another separate point B. For example, an amount of energy could, did I read that? The total amount of some conserved quantity in the universe could remain unchanged if an equal amount were to appear at one point A and simultaneously disappear from another separate point in point B. I read that wrong. The total amount of some conserved quantity in the universe could remain unchanged if an equal amount were to appear at one point A simultaneously disappear from another separate point B. So you're talking about the universe as a closed or an open system. You're talking about it as a closed system. The universe is a closed system, but it's not. We know it's not. Yes, it's isotropic. No, it's not infinite though, because we got a finite border of the universe as if it were a galaxy. But you're talking about like some teleporting thing. For example, an amount of energy could appear on Earth without changing the total amount in the universe if the same amount of energy were to disappear from some other region in the universe. So you're just teleporting from one thing to another. That's still conservation of energy. This weak form of global conservation is not really a Why are you mentioning this at all then? This weak form of global conservation is really not a conservation law because it is not Lorentz invariant. So phenomena like the above do not occur in nature. I don't know what a Lorentz invariant is. Due to special relativity, if the appearance of the energy at A and the disappearance of energy at B are simultaneous in one inertial reference frame, I don't know what that means, they will not be simultaneous in other inertial reference frames moving with respect to the first. I'm not going to try to understand that right this second. In a moving frame, one will occur before the other. Either the energy at A will appear before or after the energy at B disappears. In both cases, during the interval, the energy will not be conserved. I still don't understand what that means. A stronger form of conservation law requires that, for the amount of a conserved quantity at a point to change, there must be a flow or flux of the quantity into or out of the point. For example, the amount of electric charge at a point is never found to change without an electric current into or out. Okay. A stronger form of conservation law requires that, for the amount of a conserved quantity at a point to change, there must be a flow or flux of the quantity into or out of the point. For example, the amount of electric charge at a point is never found to change without an electric current into or out of the point that carries the difference in charge. Since it only involves, okay, I understand that. Since it only involves continuous local changes, this stronger type of conservation law is Lorentz invariant. So the first one is talking about a teleportation within a gigantic global system. The other one is talking about something that's changing locally. In other words, like immediately next to it, like adjacent to it. There's continuity. There's flux. There's a flow from one thing to another. For example, the amount of electric charge at a point is never found, blah blah blah. Since it only involves continuous local changes, this stronger type of conservation law is Lorentz invariant. A quantity conserved in one reference frame is conserved in all moving reference frames. Well, I still don't know what local means. I don't know what reference frames are. This is called a local conservation law. Local conservation also implies global conservation, that the total amount of the conserved quantity in the universe remains constant. All the conservation laws listed above are local conservation laws. A local conservation law is expressed mathematically by a continuity equation, which states that the change in the quantity in a volume is equal to that of the total net flux. I'm drifting off again. I don't understand. Which states that the change in the quantity of a volume, which states that the change in the quantity in a volume, not of a volume, which states that the change in the quantity in the volume is equal to the total net flux of the quantity through the surface of the volume. Why are you talking about surfaces when you were talking about volumes? Or I thought you were talking about like the contents of a space, like a 1 meter sphere, an imaginary sphere surrounding an arrow, or the arrow, its volume is the arrow itself, right? So the volume of the arrow is equal to like the dimensions of the arrow. Why are you talking about the surface though? It's not my fault that learning is so hard. It's that teachers are bad. This is a bad teacher. Wikipedia is being a not good teacher. They're just poor teachers. They're bad at teaching. This does not need to be that difficult. Which states that the change in the quantity in a volume is equal to the total net flux. We're not talking about like the flux stuff that you put on like solder stuff. We're not talking about that kind of flux. The following sections discuss continuity equations in general. Differential forms. That is an image. Why do they have this as an image instead of as Unicode? Because I know they made that image using Unicode, right? Unicode characters. I don't think I should bother going into the differential forms when I don't even understand momentum. In continuum mechanics, see also conservation form and continuity equation. In continuum mechanics, the most general form of an exact conservation law is given by a continuity equation. For example, conservation of electric charge Q is, and then they give stuff that's just a blob because they don't define any of this stuff. But they're going to define it. Why did they not talk about that weird delta thing? So where do I need to start? Momentum. Maybe I need to start by just giving up and going to bed. Newtonian mechanics. Now we're okay, so we've pretty much read through the article on conservation laws. There's a bunch of equations and stuff, but I think until I learn about momentum and all this other previous stuff, I'm not going to be able to understand that. Echo. Set a reminder for 10 a.m.
What's the reminder for?
Go pick up groceries.
Okay, I'll remind you at 10 a.m.
Momentum is a short article. Nope, I was not right about that. I was looking at the scroll thing at the side of Wikipedia that talks about like the different tools you can use on the article, not the gigantic. Like this is a book. I'm frustrated. I just want to learn about freaking quantum physics. Why is it so difficult? This is like the most basic things that should be the simplest things. I don't know how I managed to get a hair in my mouth. I can't think straight anymore. In Newtonian mechanics, momentum, more specifically linear momentum. In Newtonian mechanics, momentum, PL. What is PL? Plural. Momenta or momentums, more specifically linear momentum or translational momentum. I know what translation is. Translation is just when you're moving something around. I know that because like that's from computer graphics. I'm gonna mute this and go brush my teeth. get started in this or not? Kind of, yes. I feel like I haven't learned anything aside from just that I've got to be redirected to this article to read to start to understand things. It's like I keep getting told that I need to learn things, and then just when they try to teach me stuff, they don't teach me anything. They just teach me that I need to go to somebody else to learn. In Newtonian mechanics, okay, I know what Newtonian is. Everybody knows who Newton is. You know the laws of thermodynamics and stuff. In Newtonian mechanics, momentum. Who was Newton's rival in calculus? I feel like we should just call it by that guy's name. In Newtonian mechanics, momentum, plural, momenta or momentums, more specifically linear momentum or translational momentum, is the product of the mass and velocity of an object. I know what mass is. Mass is the chunk. I know what velocity is. Velocity is the speed. It is a vector quantity. I don't know what a vector is. I know what vector art is. Vector art is when you've got like a curve. It is a vector quantity processing a magnitude and direction. How much and where? Let's just double check and make sure I know what I'm talking about. In mathematics, physics, and engineering, a Euclidean vector, or simply a vector, sometimes called geometric vector or spatial vector, is a geometric object that has magnitude, or length, and direction. Euclidean vectors can be added and scaled to form a vector space. I don't know what a vector space is. A vector quantity is a vector valued physical quantity, including units of measurement and possibly a support, formulated as a directed line segment. A vector is frequently depicted graphically as an arrow connecting an initial point A with a terminal point B, denoted by, and then it shows AB with an arrow superscripted over the top of it. If they're going to call B a point, why don't they have a point at B instead of just an arrow? Because if you've got B going off, if you've got an arrow going off somewhere, you're saying that it continues past B. Okay, fine. So the first word they mentioned was magnitude, so let's look up magnitude. This is a long article again. In mathematics, magnitude or size of a mathematical object is a property which determines whether the object is larger or smaller than the objects of the same kind. I can understand that. Big and small stuff, right? Let's see if I can understand this. I'm not gonna go for too much longer. I think maybe I'll go for another 11 minutes and then give up. Just next time I'll have to pick up with magnitude and mathematics. See if maybe it's possible for me to understand this. I don't know if I can do this. You know, I keep thinking that maybe I'm the stupid one, but these people writing this stuff are so bad at explaining this that I'm thinking maybe they're the stupid ones. It's like, yeah, you understand it because you studied it for years, but you can't communicate it back to other people, so are you really that smart? Maybe you're just good at learning stuff, but you're bad at communicating it. Okay, let's just try to read. I said I'd go for like 10 minutes, so now that's turned into like 9 minutes. More formally, an object's magnitude is the displayed result of an ordering or ranking of the class of objects to which it belongs. I understand what order is. You put the stuff next to each other. Magnitude as a concept dates to ancient Greece and has been applied to it as a measure of distance from one object to another. For example, the absolute value of a number is commonly applied as the measure of units between a number and zero. Okay, I know what zero is. Do they ever talk about zero in Sesame Street? I know they talk about the positive integers and everything, but I don't know if they talk about zero ever. In vector spaces, the Euclidean norm. What's the Euclidean norm? We didn't define what a vector is. Wait. We get redirected from Euclidean vector to magnitude, and now they're saying the Euclidean norm. Oh, they're about to define it. They're going to say what it is. In vector spaces, the Euclidean norm, so this is what a Euclidean norm is. In vector spaces, the Euclidean norm is a measure of magnitude used to define distance between 2 points in space. Why don't you just say distance then? So you've got a distance between two objects. And you're saying that's the Euclidean norm? Why don't you just say distance then? What's the difference between that and distance? In physics, magnitude can be defined as a quantity or distance. An order of magnitude is typically defined as a unit of distance from one number and another number's numerical places on the decimal scale. So I guess we're going to have to learn about the Euclidean norm, Euclidean space. vector space E is associated to a Euclidean space E in inner product. Okay, the vector space capital E with an arrow over it associated to a Euclidean space capital E, both of these are italicized, is an inner product space. What's an inner product space? This implies symmetric bilinear form. What is inner product space? In mathematics, oh my goodness, look how long this article is. I'm never going to understand any of this. Wait, this is linear algebra. I know what this is. In mathematics, an inner product space is a real vector space. What's a real vector space? Or a complex vector space with an operation called an inner product. Okay, so what's it says, or rarely a Hausdorff pre-Hilbert space. Well, if it's rarely, we'll learn about it later. Is a real vector space. All right, what is a vector space? In mathematics and physics, a vector space is a set whose elements, often called vectors, so help me if this redirects to the same article. Man, we've got a circular thingy. We've got a circular redirect. So we go from Euclidean vector to magnitude to vector space to vector back to Euclidean vector. They're not defining anything. They're not saying what any of this stuff is. Is it a half hour? Has it been an hour and a half yet? Can I stop this? The term vector is also used in some contexts for tuples, which are finite sequences of a fixed length. As in like octuple. maybe I have to learn about vectors first before I can learn about vector spaces. In mathematics and physics, vector is a term that refers to quantities that cannot be expressed by a single number, a scalar. We didn't learn about scalars yet. Scalar quantities, or simply scalars, are physical quantities that can be described by a single pure number, a scalar. Oh boy, it's referring to mathematics. Typically a real number, accompanied by a unit of measurement, as in 10 centimeters, 10 cm. Examples of scalar are length, mass, charge, volume, and time. Scalars may represent the magnitude of physical quantities such as speed is to velocity. So speed and velocity are not synonymous. You'd say the velocity is x speed. Scalars do not represent a direction. Scalars are unaffected by changes to vector space basis, i.e. a coordinate rotation, but may be affected by translations as in a relative speed. The change of a vector space basis changes the description of a vector in terms of the basis. In terms of the basis used, but does not change the vector itself, while a scalar has nothing to do with this change. In classical physics, like Newtonian physics, rotations and reflections preserve scalars, while in relativity, Lorentz transformations or space-time translations preserve scalars. The term scalar has an origin in the multiplication of vectors by unitless scalar, which is a uniform scaling transformation. A scalar in physics. This is actually a short article, so maybe I can come back to it. Alright, so we're abandoning ship and going to look up scalars in mathematics. This is actually a pretty short article. That looks a lot like French. That kind of makes sense. A scalar is an element of a field which is used to define a vector space. In linear algebra, well, we're going to have to look up fields now. And this is an insanely long article. understand addition, subtraction, multiplication, and division. I understand those things. Behave on rational and real numbers. I understand what rational and real numbers are. In mathematics, a field is a set on which addition, subtraction, multiplication, and division are defined and behave as the corresponding operations on rational and real numbers. I understand that sentence. A field is thus a fundamental algebraic structure. I know what algebra is, which is widely used in algebra, number theory, and many other areas of mathematics. And I know what number theory is because I know what numbers are, I think. Number theory is a branch of pure mathematics devoted to the study of integers and arithmetic functions. Number theorists study prime numbers as well as the properties of mathematical objects constructed from integers, for example, rational numbers, or defined as generalizations of integers, for example, algebraic integers. In algebraic number theory, and now I'm redirected to algebraic integers. In algebraic number theory, an algebraic integer is a complex number that is integral over the integers. Integral. That is, an algebraic integer is a complex root of some monic polynomial. A polynomial whose leading coefficient is 1. What is a coefficient? Whose coefficients are integers. The set of all algebraic integers, capital A that's italicized, is closed under addition, subtraction, and multiplication, and is therefore commutative, a commutative subring of the complex numbers. Okay, now I'm lost again. What are complex numbers again? A complex number is a number of the number system. In mathematics, a complex number is an element of the number system that extends the real numbers with a specified element, denoted I, called the imaginary unit, and satisfying the equation I squared is equal to negative 1. Every complex number can be described in the form a plus bi, where a and b are real numbers. So 1 plus 1i, which would be 2i, no. I'm going to have to learn more. I'm going to have to refresh myself on algebra, aren't I? think I'm gonna stop at least. Stop at least here. I could pick up by reading about the imaginary unit in math, maybe, or reading about electronics and see if maybe I can make them make sense without getting into all this other stuff.